Good afternoon. Today we're actually going to go back and talk about another type of force that we haven't talked about yet all year. The reason I waited until now is so that we are in the electricity unit and you could have a better understanding of the sorts of quantities that I'm going to throw at you that make up this force. We're going to talk today about something called the electrostatic force. And in order to start talking about the electrostatic force, I do apologize. I wish I had the ability to do this demonstration for you, but I would set this up in my classroom if I were there, and what it would be two balloons, each tied to a string, hanging from a bar, and the balloons would not be hanging straight down. They would actually look like this. One would be kind of at an angle this way, one would be kind of at an angle this way, and you would walk in and you would see this. You would be like, well, why are they hanging like that? That looks kind of weird. Well, knowing what we know about electric charge, you could probably guess that one of the reasons the balloons might be hanging like this, whereas normally they would be hanging straight down, is perhaps they have some electric charge on them. Specifically, perhaps each balloon has the same type of charge on them, because as you remember, like charges will repel. Sorry, notification from my computer. Like charges repel each other, opposite charges attract. So why are the balloons separated like this in this picture? Well, they are repelling each other. Because they have the same charge sign. Either both balloons have a positive charge or both balloons have a negative charge. Now, what would that charge, or what would that free body diagram look like if we wanted to know about the forces on those balloons? Well, I could draw one. Here's our balloon. We need an axis, of course. X, Y, those are the positive directions. Now, balloons have mass. We know that there would be a force of gravity pointing downward like this. We know that they're attached to a string, which would provide tension for the balloon. But so far, this doesn't explain why they would be separated like this. From this perspective, it almost looks like the balloon should be accelerating, if not up or down, definitely to the right. Well, the reason the balloons are spread out like this is because there is a force between them. That force is called the electrostatic force. You can tell that I'm drawing the free body diagram for the leftmost balloon right now. The electrostatic force repels the balloons away from each other, so the force on this leftmost balloon must be pushing it to the left, like so. The symbol for this new force, the electrostatic force, is Fe. Without ever touching, okay, so let me back up. I could go into a more in-depth free body diagram here and write some net force equations. I'm going to save that for just a little bit at least. Without ever touching, the balloons exert a force on each other due to the fact that they are electrically charged. What sort of factors do you think determine the size of this force? Well, if you think about it, you might say, well, how big the force is probably depends on how much charge each balloon has. Okay, if there was more charge, ideally there'd probably be a bigger force. There'd be more charges repelling. That would be a stronger force of repulsion. So how much charge is on each balloon definitely seems like it should be a factor. Another factor might be, well, okay, the two balloons are repelling right there. What if I move them really far apart? Is distance a factor? And it turns out that it is. The other factor is how far apart the balloons are. So these factors were investigated by scientists and physicists, and what came out of this was an equation that tells us how big the electrostatic force is between two charged objects. It has a name. It's called Coulomb's law. Coulomb's law is the equation for the force between two electrically charged point objects, and I'll explain what a point charge is, or a point object is, in just a little bit. But let me show you what Coulomb's law is first. I did manage to get a copy of the reference tables. So real quick, while we've been missing some things, let me just go over what we now know. Let's see here. Okay, so we already talked about this. Speed of light we'll get to, speed of sound we'll get to, masses of the Earth, Moon, radii, distances. Okay, we're going to talk about this today in just a minute. One elementary charge, 1.6 times 10 to the 19th coulombs. 1 coulomb is 6.25 times 10 to the 18th elementary charges. Remember, these numbers are inverses of each other. Electron volt later, Planck's constant later. Okay. universal mass unit later. These are the masses of the electron, proton, and neutron. They come up a few times in this unit, but not that much. Let's see, what else have we talked about? Nothing here yet. This is the page we'll be on today. Always good to look at some geometry stuff. There's the geometry stuff if you didn't know. I think there might be a couple equations on this that we haven't quite gone over yet, or we weren't around for in person. I'm thinking all this stuff looks like we got through it. Potentially this equation. I can't remember if we did this in class or not, but the other energy equations down here. Okay, so all the things that we've been talking about, they are on the reference tables. Let's go back to page 4. Page 4 has this nice electricity section, okay? Basically, the whole page is electricity. Today, we're just going to be starting with the equation at the very, very top, okay? This equation right here, Fe equals K Q1 Q2 over R squared. So let's write that down. Again, this is on page 4. Fe equals K Q1 Q2 over R squared. And let's label what everything means. Fe is the electrostatic force. You see it right there. K, now this is what I was just talking about a minute ago. K is the electrostatic constant. And whenever you see constant, that usually means it's on the front of the reference table. So let's go to page 1 on the reference tables. And it is right about in the middle, right where it says electrostatic constant. Symbol is K. The value is 8.99 times 10 to the 9th newtons times meters squared over coulombs squared. Electrostatic constant. And the value, again, 8.99 times 10 to the 9th newtons times meters squared over coulombs squared. And yes, you do need to write the units each time, okay? You do need to write the units each time. Not that big of a deal because they're given for you right on the reference table, right there. Q1 and Q2. If we look in the reference table for Q under the electricity section, notice these are lowercase q's, not uppercase q's like thermal energy or internal energy. Q stands for charge, okay? So Q1 is charge 1, Q2 is charge 2. This is the force between two electric charges. You can't have a force between just one electric charge. It has to be an interaction between two objects. Remember, all forces are between two objects. So these are electric charges. And I have two very important notes about this. Electric charges must, in this equation, be in coulombs. If you're given an electric charge in elementary charge units, you need to convert it to coulombs before you use this equation. In addition, when plugging into this equation, you will use the magnitude only of the charge only. Not the sign. Doesn't matter if it's a negative charge, okay? You take that negative sign off and you put it into the equation. You can always tell later on whether the force is attractive, brings things together, or repulsive, pushes things away, by what type of charges you plugged in. I'm not saying ignore if it's a negative. I'm just saying in the equation, the negative will not go into the equation, okay? Don't put the negative in the equation. Just remember that one of those charges is negative, or one or both of the charges is negative, and list the force as attractive or repulsive, respectively. The last part of this equation, R, is similar, it's a lowercase r again, is similar to how you've used it in the past, the distance between the centers. Not specifically the radius, it is the distance between centers of charge. Okay, so if you have two charges here and here, it's not the distance between their surfaces. It's the distance between the centers of each charge, and that matters sometimes. Now, looking at this equation, this looks kind of similar, right? It's something times something times something over r squared. Doesn't it look kind of like this equation right here? The universal gravitation equation? It should. it looks similar to the gravity equation, which, to refresh your memory, is Fg equals g m1 m2 over r squared. And now this isn't very important for this course. It is kind of interesting that they look similar, but this is much more important when you start to think about the advancement of physics in general. The fact that these two equations are similar has actually led scientists, recent scientists, people in the last 100 years or so, on some very interesting paths that we'll get into at the very end of the year. The fact that these two equations are so similar makes people think that, maybe they are somehow related. Even though gravity and electricity seem very, very different, maybe there's some sort of link between them. Okay? So we'll talk about that again at the end of the year, but I just wanted to point that out. It is very interesting that these equations are so similar. Points to maybe an underlying relationship between them. Moving on, this law, Coulomb's law, it works best in a couple different cases, very simple cases that you'll see a lot of. It works best for what we call point charges, especially electrons and protons, but also any other physically small charges. In other words, little tiny objects. Okay? A point charge is something that's just very, very small. It's like a point. A mathematical point is one-dimensional. It's very, very small. That's what we mean by point charges. Electrons and protons are so small that they more or less qualify as point charges. This law also works very well for spherical objects, objects that are spheres. The reason it works well for spherical objects is because you can always imagine that they are points. You can imagine taking the sphere and kind of shrinking it down until it's the size of a point. And so a sphere kind of acts like a point in that sort of sense. Other types of objects that aren't spherical or aren't point objects, very small objects, this doesn't work as well for, but you won't have to really worry about that, okay? If you take, let's say, a college-level electricity and magnetism class, possibly, but we're not quite there yet, okay? Now, when using this, if the charged objects are of similar signs, meaning Q1 and Q2, they're both positive or both negative, then the force will be repulsive. In other words, the two objects will repel each other. It's not that one object stays still and the other object repels away, unless you're holding one in place. They repel each other. Both of them try and move away from each other. If there are different signs, one's positive, one's negative, then the force will be attractive. So, you don't plug the signs into this equation, but you do think about the signs of the charges. Even though you don't plug them into the equation, if the signs are the same, the force is repulsive. If the signs are different, they are attractive. What I would do now, and I have offered this for, I will. I have offered this for extra credit in the past. Determine the product of the charge on the balloons. What I'm going to suggest that you do is, if you have access to balloons somehow, or you have access to and string and something to hang them from, it would be really cool to see if anyone could actually do this. To see if anyone could actually make this sort of setup with the two balloons repelling each other, hanging from the same point, and then figure out a way to determine the charge on the two balloons. What you're going to need to do, I'll give you a couple pointers, is continue setting up this free body diagram, write some net force equations, and basically solve down to the level where you have Q1 times Q2, the product of the charge on the balloons, being equal to something, okay, equal to some big algebraic mess. I'm going to give you a hint. As far as the variables go that play a role in this relationship, some of the variables, I'm not saying the constants, but some of the variables you might need are the balloon mass, the angle that they make with, let's say, a vertical line, and the distance between the centers. Okay? So if anyone's interested in looking at that, I'd be more than happy to take a look at what you do and maybe point you on the way if you're so interested. I would want to see a picture of your setup as well. I don't want this just to be a mathematical problem. I want to see if you can actually do it. Okay? In my next video, we'll actually use this equation a couple times. We'll get used to how it's used, and then I think we'll be done with electrostatic force after that. Okay?